there's a lot of geophysical flows, and I like to think of them as a gradient from being essentially purely or strongly granular, all the way to being hydrodynamically driven, where I use hydrodynamic in a broad sense. That can mean any continuum fluid, that can be air. And of course, there are other multiphase flows that we can think about besides fluid and particles, but I'm going to be talking about fluid and particle ones today. And Karen and I wrote what you could call a manifesto a couple years ago, which was an attempt to try to bring a consideration of the soft matter or the material considerations of the Earth into consideration in thinking about some of these geophysical flows. And one way to collect thinking about these geophysical flows is along two axes that by now are probably pretty familiar to people in the audience. The y-axis is a solid volume fraction, so this is just the volume of particles compared to the total volume occupied by particles plus pore space, whether they're filled with water or air or some other thing. And on the x-axis here is a dimensionless shear rate. It could be I, it could be J, it could be some other one. If you don't like thinking about that or you're still new to that rheology game, you could also think of it as just an inverse viscosity, right? And so overcrowded in this corner in the top, we see something like soil, which is apparently solid. It has an elastic modulus. It can behave as a solid by all definitions. It still does some strange things that I'm going to talk about. But if you shear that material and you dilate it a little bit, you can lower the volume fraction just a little bit, and that soil can suddenly liquefy and fail and flow. And as you either increase the shear rate and you have more flowing materials, you can think of essentially marching down this curve toward higher shear and more dilute kind of conditions. So landslides, you mix with water, you get debris flows moving down. You have pyroclastic density currents and lahars and rivers and things. And that gray line is just a line to guide the eye. But by the way, that line is something like an abstraction of the Boyer et al. Type relation, right? So if you think of like a J, phi kind of thing, so you can think of that the flows that collect along that line are probably flows that are frictional granular materials and suspensions. There are some out in nature that are not frictional, right? And they don't fall on that line, okay? And so Kyle was talking about flocculating particles and clays. If you start getting sticky materials like mud that can make gels, you can make things that are solid-like at even very low volume fractions. I'm not going to talk about those today, but I am happy to talk about them. We like them. So in 2018, as Jeff mentioned, there was a KITP program that was wonderful, the physics of dense suspensions, and there was also a terrifying and catastrophic dense suspension that happened at the same time. And the short summary, if you don't know much about it, is that this is kind of the common wildfire debris flow thing that happens. There's a big intense fire in late December 2017, burned all of the vegetation, left a bunch of loose soil. Then 3 weeks later, there was a really intense rain that happened. The hillsides in the mountains turned to a liquid mud. They came down and collected into valleys and picked up boulders, and they flowed out of those canyons, and they buried a neighborhood in Montecito with boulders, killed 23 people. And then the mud jumped over the boulders and kept flowing for kilometers down a road, basically, into the 101, which is the picture you see on the bottom. And so Shravan has a great poster on the rheology of these materials. And I'm not going to go into a bunch of detail about it, but I do want to talk about some essential elements of this that are related to some of the other components people brought up in the talk, right? And so in 2018, when these debris flows happened, a few of us, led by Tom Dunn, who's now emeritus faculty here at UCSB, went up into the mountains, and the basic idea was we were interested in why some materials on some hillsides created the mud that made the debris flows, but in other watersheds, that material did not contribute to making the mudslides, right? So we went into the headwaters, we went into the place where the source materials that made the debris flows came from, and we took a bunch of samples. That's what all those little dots are. And so if you're not used to looking at topographic geologic maps, the different faint stripes there are just different rock units. And the little yellow dots are just places where we took samples. These are really steep headwater streams. And if you sample this stuff, okay, this is nasty stuff. I don't mean nasty like it'll make you sick, but I mean if you're in the physics side of doing rheology. That's a particle size distribution. The black line is just a random measure of soil from one hillside. And you can see that it has everything from clay to very coarse sand and even small gravel. A lot of the samples are bimodal, some of them are trimodal, so you have clay, you have silt, you have sand, you have a little bit of gravel. You know, if you're going to do the normal like physics engineering thing, we fit a log normal to it so we can describe its polydispersity in a simple way. But these are really nasty, widely distributed materials. They've got organic material in them, all kinds of stuff. What we do is we do a little bit of parallel plate rheometry though, so we take these samples back to the lab, where you reconstitute them. We take dry samples and we add water to them at different volume fractions. And we stick them in a rheometer, and we shear them, and we're trying to understand, is there something about the material differences among these soils that can explain something about their different flow behavior. And by the way, so we put this material in a parallel plate rheometer. The maximum Reynolds numbers we get at the highest shear rates are about 10, but they're usually around 1 in the rheometer. The maximum Stokes numbers are about 1, and so these are laminar viscous flows inside the container. If you ask about the flows out in nature, they were more like Reynolds number 50 to 100, and they were Stokes number somewhere in the range of 5 to maybe 10, right? And so we're not exactly at the conditions in the field, right? But at least for our rheology, yes, Michael.
And why deionized water? Does it matter?
Only for reproducibility. So there's clay and organic material in here, so we do expect that some component of ionic strength or other structural interactions could influence aggregation. And the tap water in Philly or anywhere else varies a little bit from day to day. And so we could have put any water, but the idea of putting DI water wasn't to represent nature, but was just to make things reproducible so that every sample we can know we added the same stuff. So you now know the deal a little bit, which is that if you take clear water and you add particles to it, it gets more and more viscous at first. Eventually, if you keep adding particles to it, those particles can start interacting with each other, first hydrodynamically, but eventually frictionally if you squeeze them together. To give you an idea up there of just taking a sample of soil and mixing it with water, so at 35% volume fraction, it still is an oozing thing. By the time you get it to 50% volume fraction, it's granulated or kind of like a paste, right? So you can see that over this range of in the top, for example, 15% increase in the water fraction, you go from fluidity to solidity. So, you know a little, if you know the deal with rheometry, this is familiar to you. If you don't, sorry, I won't go into much detail, but you take some of the stuff, you chuck it in a rheometer, you do a steady shear rheology flow curve, so shear rate against the shear stress against the shear rate. You take one sample and you put it in, and we reconstitute it at different volume fractions. And of course, you can see that as you increase the volume fraction, the overall resisting stress goes up. I'm not showing the lower volume fractions. For low volume fractions, you have a Newtonian behavior. As you increase the volume fraction, you see that you pick up a yield stress, right? So there's the emergence of a yield stress, and in this material, that has a lot to do with the fact that there's clay and sticky material in it. So at low shear rates, you have a yield stress, which we'll call tau 0, right? Which is arising principally because of the cohesion in these materials. But if you shear the hell out of them, you see that at high shear rates, they converge toward a Newtonian behavior. The material is totally homogenized, and it's flowing like a Newtonian viscous fluid. Just to give you an idea that things are behaving in ways that we think we understand now, we can take the viscosity and look explicitly at its dependence of volume fraction. And if we plot phi m minus phi, so this is like a fitting parameter, which is our jamming fraction, right? This is the volume fraction at which the material won't flow. And if we plot the viscosity for all of our different soils from all of our different materials against the distance from jamming, we see that they collapse on that -2 curve, the Boyer curve, right? And so the viscosity does diverge as a function of the distance from jamming, but importantly, phi m is a material property that is different for each sample, right? So each material has its own phi m, and that phi m that each one has depends on a lot of properties of that sample. So thinking about what is governing these kind of suspensions, so if you look at all the flow curves for all the samples of all the different soils for volume fractions that are significant enough to have a yield stress, you see all they are in the top left. We've got a bunch of different flow curves. But the idea is that, and this was an idea proposed by Cousteau back in '95 for sticky suspensions, which is that if there's enough stickiness for there to be a significant yield stress, that essentially at low shear rates, you have a behavior that is governed by the yield stress and a resistance governed by that yield stress. But if you can overcome that stickiness and break them apart, that at high shear rates, you should get essentially a viscous flow, right? And so we do a non-dimensionalization, and our non-dimensionalization is not by J, right, which would be a shear rate, a shear rate competing with some kind of confining pressure, right? What we have is a gamma, which is a viscous stress, right, divided by the yield stress. But importantly, the viscous stress includes that volume fraction dependent viscosity, right? And so the idea then is that we think about this flow, and these are basically a frictional granular material that is a little bit sticky, which means that at low shear rates, it's governed by the stickiness, but at high shear rates, it's just a normal old frictional granular material. And so when we non-dimensionalize these curves, each with their own yield stress and each with a viscosity that depends on the distance from jamming, they all collapse, right? They all collapse onto a simple flow curve. And so this may not hold if there's some other material, if it's not sticky enough and it doesn't have a yield stress. But the point is that we can collapse all the variation in these flow curves with a couple parameters that are physically meaningful. The jamming fraction, I said, changes with each bag of soil that we have. Principally, the jamming fraction is controlled by polydispersity. We have some figures to show you for that, but I don't have time to put them in here, so I put it up here so you'd ask me about it. The yield stress is influenced by the clay content, and so we were able to rationalize at least, or tame the complex rheology of these nasty materials with a small number of parameters. But steady shear rheology is fine. But what does it say about how material fails, right? So part of my talk is not to tell you what we have done. It's to throw out some questions for you to please help me, right? The first one is that why are some failures catastrophic and others are not? And so I'll play this movie again. This is an example of a different landslide. This is in Big Sur, California in 2017. So it's raining. You see the time flying by up in the corner. This is over a period of half a year. It rains and it dries and it rains and it dries. And these colors are related to ground motion. Okay? And so in this case, this is kind of a classic landslide scenario where you rain on the soil and it creeps a little faster, and then it dries and it slows down, and you rain on the soil and it creeps a little faster. But then when these creeping regions link up and percolate, at some point the material fails, right? And so this is the Big Sur landslide before landsliding and after. This is a classic catastrophic failure. This is not what happened in Montecito. Okay, in Montecito, if you go to the hillsides that were burned, these are the areas that made the mud. You see that there are these little rills that are in here, and by the time you get to the bottom of the hillsides, these rills actually have levees and yield stress viscous flow features in them. What happened on this hillside is that it rained like hell. The clear water entrained soil progressively down the slope, and you can see this when you look at the morphology of the channels. There was no place where there was a catastrophic landslide. Instead, you had clear water progressively entraining and mixing with soil gradually, so that these flows basically bulked up and approached the jamming point as they built up down the mountain, right? And so the question that we've been wrestling with and we have no good answer for, we know how much water came and rained on the mountain. We know how this material flows at different volume fractions, but we can't come up with a way to mix the water and the solids progressively so that they will do this without catastrophically failing, okay? And so, of course, the flow that was produced was catastrophic, but don't think this was a landslide. You had a bunch of little rills that were little garden hoses of mud filling the canyons, and it's only because all those little garden hoses of mud merged together that it made it fail, okay? So that's one thing we don't understand. But just to map it onto this space, so Jeff had mentioned this beautiful paper recently from Wilson Poon's group. If you think about particles mixed in water, if you have a really high volume fraction above some critical volume fraction, which is we typically associate with random close pack, a material is always jammed, right? So you take a suspension, and if you make the volume fraction really high, no matter the stress, the particles can't flow past each other. It's always jammed. But below some other minimum volume fraction, which is the phi m here, if you have a mixture of particles in water, it will always flow, even if the stress is 0, right? But in between, you have this nether region where the material can be flowing or it can be jammed, and it depends on how much stress you're applying to the material, right? And this connects to some of the ideas of shear jamming or even shear thickening that has been mentioned previously. So if you want to then think about this in terms of the landslides we looked at, so the Big Sur landslide, you had a situation where it rained, the rain saturated the soil, it reduced the effective pressure, and so you can think that for sure the stress went down. The volume fraction may have gone down. Presumably it went down at least a little bit right at the point of failure, so that failure, say at the Big Sur landslide, would have done something like this. But for the Montecito debris flows, we had mostly a constant stress condition. The stress may have changed a little bit. We don't really know. But for sure, we know that the volume fraction of these flows started out as clear water rain and then it progressively moved from left to right. So another question I want to raise then is on mud and boulders. So we know that the mud came off the hillsides. We know that these mud flows pick up boulders from the channel bottom. And so we create a boulder-rich dam in the front. This is the Illgraben again. You can pick up boulders that are up to car size, but behind it is a dense, viscous mud pond, essentially. And so the way that a lot of these debris flows move is the boulders are in the front, and you could either think that the flow is pushing the boulders, or that the boulders are moving and holding up the mud ocean behind it, right? Here's the thing. We don't even know, for Montecito or other debris flows, whether the separation of boulders to the front is a granular phenomenon or a phase separation phenomenon. What I mean is that if you have dry granular materials and you shear them, of course you have this Brazil nut effect kind of thing. The coarse grains float to the top. There's actually a lift force on them. And because you have a velocity profile, the grains that float to the top get delivered to the front because the flow at the top is the fastest. And you will separate grains and make a coarse front that way. However, if you have a viscous liquid and you put particles in it in a suspension and you run it down a steep slope, you will also get a phase separation where the particles will actually move out to the front and separate from the liquid, basically because the particles are both feeling the drag of the liquid and also the gravity acting on them. And so if you think about it, depending on how wet or dry the debris flow is, you could have a separation that is either a granular phenomenon or a phase separation phenomenon or something in between. Okay, so now we get to the fun part, which is the granular solid. And is anything really truly jammed? And of course, we've heard a little bit about creep. Now, I like to think of creep as the seedy underbelly of the jammed state, because underneath of jammed, there isn't supposed to be anything interesting there, but you just have to look, right? And so the subcritical granular fluid system, so below yield, below the critical point, granular materials creep. And I want to talk about, so first, it's one way to think about creep is if you have a system that is thermally influenced, right? So there's something that can cause the particles to jiggle. In glasses, this is the case. Then it makes sense that creep happens. In this beautiful experiment by Beirut et al., what they did was they put particles in a drum and they tilted it at an angle, but these were actually colloidal particles that were sitting inside of a liquid. And so they were small enough to get to be thermally jiggled. And so what you find then is that the pile will relax the slope angle, and the slope angle relaxes, right? And it depends on how thermal the particles are, right? So the smallest particles are most thermally influenced, and the pile relaxes quickly. But as you increase the size of the particles, it relaxes more slowly. Morgan Husset, working with Jeff Morse, they did a beautiful experiment to translate this to a granular system. So now you're looking at sand-sized particles, no thermal influence, but they tilted at an angle, and they said, well, if we wanted to mimic something like thermal influence, how about if we put a liquid flow up through the bottom? So we have a heterogeneous system, and we're pushing it with liquid, and of course, as you start to drive the system harder, it starts to creep, and they found that the slope angle diminishes, just like this thermal system, which now we said, let's take it all out. No thermal, no fluid, no nothing. We just want to pour a pile of sand on the table, let it sit there. Could you imagine proposing this to a PhD student? Nicole loved it. So you pour the pile of sand and you let it sit there, but you use this diffusing wave spectroscopy technique, which is beautifully laid out in this review by Axel Amann, who helped us out a lot in setting this up. And it allows you to see displacements on the wavelength of the order of the light. And here's what I want to show you. This is a movie viewed through diffusive wave spectroscopy of a pile of sand sitting on a table. It's not doing nothing. It is a writhing sea of motion, right? This is what a damn sand pile on a table is doing, right? So all of these little popcorns that you see, this is a map of instantaneous strain rate, okay? So these are all little zones of rearrangements popping off. If you look at the average creep rate, it diminishes through time as the pile ages, but it will keep creeping as long as you allow it. And so this is what the pile looks like at a moment of preparation. It's loose and fluffy, and it's creeping like this. This is what it looks like after 11 days, right? Perfect. And so what I want to leave you with is that this pile is relaxing under gravity. It's slowing down as a power law function of time. This is a common behavior that we see in glasses. And by the way, some people have mentioned this. If you look at how the creep rate diminishes from the surface of the pile down deep, it diminishes exponentially, which is not a smoking gun of anything, but we also see exponential creep rate profiles in hill slope soils. And the mystery that I'm going to leave you with is, which has been asked me many times, is what are the origins of creep? Why is the pile sitting on the table creeping? So thanks for your attention.
Questions, and I'll remind people to use the microphone. Jeff?
Thank you, Michael. Well, thank you very much, Doug. That was nice. Can you hear me? Yeah, okay. So one comment as a card-carrying rheologist, I think the gamma parameter that you used at the beginning is either a Bingham number or an inverse.
It's an inverse Bingham number.
Inverse
precisely.
Number. Okay.
Yes.
So just so you can connect with some of those people who don't think about this the same way.
I took it off the slide because I was like, maybe for 2/3 of the room, the Bingham number doesn't mean anything, but yeah.
Right. There was a I had a more physics comment, but I think I may have forgotten it now that
I have that effect on people.
I'll come back.
People that have good scary physics comments, I try to. Oh no, here he comes.
Sorry about that. It had to do with. Oh, okay. So, how much of what you see in the creep with the Nicole's experiments do you think is due to the fact that you just have very, very weakly stable contact points? And how could you change that maybe by changing the shape of the particles so that they had more flat against each other, for example, or something like that?
Here we are, backup slide. So we can do this on other materials. The problem, I will say straight up, is that, so the whole DWS thing, you see these speckles, right? And then the speckles decorrelate. So what we directly measure is a decorrelation function of the interference pattern. If you know perfectly the optical properties of the particles, you can turn this correlation function into a strain. But if you don't know or control the optical properties really well, you can look at relative differences in strain, but you become unmoored from the optical theory that allows us, because we don't know the mean free path. So what Nicole did was we looked at a bunch of different materials, right? Because people ask this question, and all of them creep, but they don't all creep in the same way. They don't all creep in the same style. So with these maps, I mean, he calls it a strain rate, but we can't really say it's a strain rate for anything other than the glass beads. But you will notice that there's some things like yeast and salt and sand that behave in a similar way. But you'll notice some weird things like the flour, which is clumpy. And as you pour it, it actually collapses several times. And those shear surfaces from the collapse become activated surfaces that perennially creep faster. So if there's an inbuilt structure, like some kind of plane of failure, that thing stays there as a hot place of creeping.
The issue that I'm raising is a little bit more to the point of, for example, does thermal motion actually matter? Because you have a place here where you just have a contact point and you're unstable, or any vibration anywhere, right? So
right.
As opposed to here where it's, it's a little bit more complex, right?
Yeah, so for sure, and Karen brought this up, like even the idea that if you go to the contact disparity scale, is anything athermal, right? Like the fact that we have the point of contact could be small enough, like nanoscale, where actually like where thermal effects are relevant. This doesn't prove that those things don't happen, but rather it doesn't prove that there's not different reasons for creep. But the interesting thing is that if you just use lamps or lights or some other acceptable DEM and you make a pile of grains and prepare them subcritical and you let them go, they also creep. Now, the point is that one thing, Jeff, though, to speak to your point, is that if you let them go, they age and they age and they age. And if you don't disturb it, it's moving into a lower energy state, right? And we know that these things compact a little bit. We also know that they're making structures that resist the direction of strain, right? And so, but it says that there's a configurational component of creep, at the very least, that's common to all of them. And then on top of that, we could have contact tribology and other things that are different in different systems. Does that make sense?
I just have two questions. Number one, have you put this, actually it's the same question, have you, which goes in this direction, have you put the whole thing on the vacuum and seen how much moisture actually matters with all this?
No, we have
because,
not.
You know, flour is very hygroscopic and, you know. And
we have not put it in a vacuum, but we submerge the whole thing, right? So we have other experiments, right? Like Pascal presented. So we have this refractive index sediment transport thing. In our case, it's an annular flume, right? And so we shear the grains with a liquid. You get a bedrock layer at the top, and you get creeping grains underneath. And in this case, and with our pile, we can also make a flowing layer where we keep adding grains so that we have a flowing layer and a creeping layer underneath. And in every way that we can measure, the creep happening in this submerged granular system is just like the creep that's happening in the dry system. By every way we can measure, I mean in things like aging and the power law rate of aging, not in the actual magnitude.
I mean, if it would be KT, right? Let's say it would really be a somewhat activated process. Then at some stage, if your grains get too large, it shouldn't matter anymore. KT will be completely irrelevant. And so if your grains get bigger and bigger and bigger and you have a cutoff at the smaller scale, it should, at some stage, these things should stop. Do you think really a huge mountain with not small grains, just a big pile of gravel, large gravel, would also creep all the time?
Absolutely. Everything is creeping all the time.
So it's the contact points. You're saying it's the contact points that break, or what? Which brings me to the next question. Have you dumped this thing in a cryostat and just see what happens when you go down in KT? Reduce KT by a factor of 100 and, you know, go down to 100 Kelvin, 50 Kelvin?
We haven't. We're busy tickling it right now, I guess I'd say. So we've decided to take the angle, which is not the only angle, but to say, okay, right now we have a noise floor, and rather than lower the noise floor, we'll accept the noise floor, but now we're going to perturb the other way.
Well, that's the other way.
So we've been driving the system.
There should be an optical cryostat at Penn, so you might just ask somebody.
In the interest of time, Michel, you get the last question, and I'll remind everyone, of course, we have great breaks and lunchtime to continue the discussion.
Well, thank you. It's the first time I see you speak, and frankly, I'm totally impressed by your enthusiasm.
Oh, thank you.
And I agree with you that this is a really important point to see creep in this way. Often the granular materials, we think of it as being the elephant in the room, you know, the mass, the center of gravity. But in fact, it's more like an elephant on roller skates. What matters really to the process is not so much the elephant as the roller skate, that is to say the grain interaction at the contact scale. So whereas the elephant doesn't care about KT, the roller skates care about KT. And in the numerical simulations, which really is a surprise, I guess, that it would also occur there. Numerical simulation, there's always noise at the numerical noise, because it goes to 10⁻⁵. So there's the KT in numerical simulation. So would it be possible if you took a computer that happened to be 64 bits rather than, let's say, 128 or 256, you might be seeing a KT effect that has to do with the contacts?
For sure. And the question I think that comes up is both deep, and sometimes completely academic, which is both. If we could eliminate all perturbations or all effective KT, would creep happen? And then we would say, do we ever have that situation? And I think both are interesting. In other words, it's not to be dismissive of the question. It's the fact that, right, as you keep trying to reduce and reduce noise, and we still have it. And I don't know how, like, zero temperature we need to be in order to eliminate it. Yeah. All right.
Thank you, Todd.